others a few more minutes and then we'll start the presentation.
That makes sense.
So while we were ironing out our, run through, Michael and I were talking about the different, like phases or problems that we've been trying to solve over the past 10 years. The first one being leaky buildings. We need to prevent water from entering, and now it's kind of phase 2, more energy consumption. And once we get those 2 problems fixed in the industry, what's going to be the next one? Does anyone have any ideas that they would want to share?
I would say embodied carbon or carbon footprint is going to be a phase of energy conservation that starts to become more prominent as understanding how to conserve energy matures a little bit.
Right.
Well, also, I think you left out airtightness. That's been an important concern for 20 years now, because airtightness controls moisture in the building enclosure as well as energy loss and gain.
Absolutely. Great point.
But I think at this point we know a lot about how to do it. It's just getting it done. Whereas the embodied carbon, well, we've had a couple of presentations where we're trying to learn what people are talking about when they're talking about that kind of thing.
It's much earlier days for that topic.
Nice to see you, Michael. Thanks for joining us.
Hello, Ryan. Good to see you. You have a very sustainable background behind you in the view. Nice out of doors.
I'm jealous. All right. Well, it is 4:31. Oh, hey, Ryan. 4:31, so we'll get started. First off, I'd like to thank everyone for joining the Boston Beck presentation. I'm Sarah Kravitz, and tonight we'll be hearing from Michael Bousfield from Cascadia Windows and Doors in the topic of understanding the benefits of high performance fenestration. And before we get started, I want to go over a few housekeeping items. So to receive AIA credits, use the link that I just posted in the chat. It's a Google form, and I also welcome you to join our LinkedIn group page, and the link's already there as well. And for upcoming events, I'm very excited to announce that the WAG-D&E Symposium on Building Science will be held on October 6th. This year's theme is Sustainable Building Enclosure, balancing building energy, performance, and durability with other building life cycle goals. So stay tuned for that. And also during this presentation, feel free to type or ask any questions in the chat, and we'll also have an opportunity at the end to go over questions as well. And just a heads up, there are polls in this presentation, so pay attention. And with that, I would like to welcome our speaker. Michael is a technical director at Cascadia Windows and Doors. He was also involved in developing the world's first passive house certified fiberglass window, as well as the world's first window wall. So thank you, Michael, for your time today and giving us this presentation.
Right on. Thank you very much, Sarah, and everybody who's joined our learning session today. I'm coming to you from the other side of the continent. I'm here in Vancouver, British Columbia right now. So it's neat that our technological point has allowed us to share amongst like-minded people like this. I'll share my screen. Sarah, I'll ask for a quick confirmation that you can see the slides in the full screen view. Is that the case?
We are good.
Excellent. And we'll get into this. So like Sarah introduced, we're going to be talking about Windows generally. We're going to be picking on some of the more well-known and less known aspects of utilizing high-performance fenestration. And before we get into the nuts and bolts of the technical side of this, I'll give a little introduction to our company so that you can form a more accurate filter for any bias that you might hear embedded in what I'm saying, because I'm with a manufacturing company and I'm going to try to be objective and educational here, but at least you'll know where I come from. So what are we going to look at today? After a really quick intro to what we do in the fenestration world, we're going to be focusing on first just the impacts of Windows to building envelope performance as a whole. We're going to understand the performance metrics and characteristics for high performance fenestration, and going to explore actually design flexibility with high performance fenestration. I'll throw in a bit of advice, a bit of examples about cost optimization, especially when it comes to Windows and Windows systems. And we'll finish up looking at some examples and case studies of high performance Windows with good U values in the real world, and what were some of the project goals, what were some of the unusual hangups that were encountered trying to achieve these results. So that is all to come. And like Sarah mentioned earlier, I invite you to please use the chat function of Zoom here for questions. And I'll ask Sarah to be the advocate of the asker, to please, if it seems logical to interrupt based on where we are in today's discussion, and ask the question, please do that. I will not be offended. I have heard this before, or most of it. We'll also have a dedicated question and answer period at the end. So real quickly, Cascadia Windows and Doors, what business does a West Coast of Canada manufacturing company have coming to the Boston Beck and talking about high performance and different types of window systems? Well, we're a manufacturer that specializes in fiberglass framed window and door products, as well as other fiberglass building enclosure products. In general, the overarching reason why we specialize in fiberglass is that it lends itself to products that can deliver better energy performance than most of the incumbent type of products. But what specifically are those products? Well, they're windows and window systems for commercial and multifamily buildings, also for smaller scale residential buildings that have more ambitious energy efficiency goals, including passive house projects, as well as an exterior insulated cladding support component that makes for a thermally improved cladding support system known as the Cascadia clip. So that's what we do. And we've noticed that over just the very recent years, there have been increased movement in the regulatory environments all across North America to more stringent energy codes and standards. And I want to touch on that and both the pros and cons with that in terms of what we do and practice in our industry. But first, I want to talk about why. And I think everybody could probably speak to this graphic for me, but I have the mic, so I'll do it. So why are building codes changing? Well, we as a society generate a whole ton of carbon emissions. We've kind of come to the scientific consensus that that's not a great deal for our future climate or our things that we desire to keep enjoying on this planet. And if you look at sources of these carbon emissions, buildings, the industry that we get to affect is actually the biggest one, even more so than, for example, all of transportation combined. And I want to do a little bit of audience interaction right off the bat here. I want to look at 3 building examples. And you know I'm going to be focusing on energy conservation here, but the way I want to do it with this audience interaction slide is that I'm going to show images of 3 buildings one after another. I'm going to give a few clues about the building's exterior. What is it comprised of? And then I'm going to start a poll with a multiple choice answers of what is the whole R value of that building's insulated exterior, the whole envelope combined. So here goes. This is building number 1. It's just over 80 years old. It's located on the West Coast, North America. It has a brick veneer that's on the outboard side of a steel stud wall. And within that steel stud wall, there is some insulation. The windows that you see, the smaller punched windows, they're not original, nor are they brand new. They're somewhere in between. And finally, those roof decks that you see also do have some insulation in them, typical for the period. So with those only few clues to help you, what would you guess is the overall R value of building number 1? All right, you should see a poll that you can vote, a multiple choice vote. And I'm going to leave that poll open another 4 or 5 seconds. Thank you everybody for interacting with the polls. It's wonderful as a speaker on a webinar situation to see that the audience shows up. Okay, I'm going to end this one. I'm going to share these results so everybody can sort of see yourself in the midst of the guesses. And we're going to go on to building number 2. So building number 2 is a multifamily high-rise, not a huge high-rise, but a high-rise nonetheless. It has a mass concrete structure. That mass concrete structure is exposed on the exterior of the building at about 50% of the area. Inboard of that mass concrete structure, where it is a wall, there is inboard of it a steel framed wall, and in the steel framed wall cavity there is R13 fiberglass batt insulation. So that's half the building exterior. The other half of the building exterior is not thermally broken, double glazed aluminum windows. Okay, let's have a guess at R value of building number 2. And these are these same choices as what you read on the poll number 1. Okay, much newer building is inspired ever so slightly more optimism from our group. I'm going to close this poll in about 3 or 4 seconds. Okay, there are the results. And finally, building number 3. Okay, so the building number 3 is a lot more modern, less than 20 years old, but it has a lot more glass. This high-rise is almost completely covered in a window wall fenestration system. That fenestration system consisting of thermally broken aluminum frames, double glazed vision glass units, and in front of the structural concrete slab of each floor level, there's a portion of the window wall system that extends down in front of the slab to cover it aesthetically and also to house a small amount of insulation in front of the slab. That slab is fully exposed in only a couple of locations, which are those vertical stacks of balconies. Okay, last one. What is the R value of building number 3? And just a couple more seconds here. We have a big range of answers, and that's very interesting. Okay, so I'm going to share these results, and everybody can again see themselves in the data. And okay, on with this. Well, I don't know whether I'm going to interest or disappoint. However, all 3 of those buildings have R values somewhere between about R2 to 3.5, which was the second guess in all of those polls. And somewhat disturbingly, the high end of that R value range is from the oldest building declining to the newest building having the lowest R value, which, whether or not that surprises you, it tells me when I was putting together this and checking the numbers, it tells me at least 2 things. Number one, as an industry, we've not been setting buildings up to be the best they can be from an energy conservation point of view. And number 2, things don't necessarily just get better with time. Like as time goes on, things don't necessarily advance. They only get better or advance if you specifically focus on it. And to some degree, in our industry, that requires a little bit of force and coercion in the form of regulations. Regulations truly need to force. And it's happening much more recently, but it is happening. Energy conservation in buildings is being built into much more effective regulatory change than ever before in just the last few years. But regulatory changes have to be based in reality. Essentially, our industry first has to have the tech, then you can change laws to require it. You can't do it the other way around. It doesn't work. And as a company, Cascadia, that produces just a little bit of that new technology, we feel we're amongst a group of companies that when that new technology becomes commonplace in the market, we're actually demonstrating that the market is ready to embrace more stringent regulations as time goes on for the eventual good of us all. Now, energy codes, no matter where they are and exactly what they consist of, they need components. And it's logical, I think, to start this conversation about windows in this learning session today, acknowledging energy conservation, because windows can play an outsized role when we're talking about energy conservation in buildings. Take an example building, a multifamily building, modern building, where you have twice as much wall as you have window. Well, maybe that's not as modern as people might think, but that's the base case for this example. These are the breakdown of the building enclosure assemblies, the walls, the roof, and the windows, and the component heat loss on each one. And you can see that a building built to ASHRAE 90.1 and a building built to a much improved standard in regards to the opaque exterior walls and roofs and other elements of the building, it still has a substantial amount of heat loss or energy loss in the form of heat loss, primarily because of the windows. And then you end up with this step towards higher performance windows. For example, this building in the second column, but with a composite frame type for the windows, we have a significant reduction in heat loss, more so in fact than the walls being more than doubled in their insulation. And yet again, we have an additional level improvement on resistance to heat loss if we go to something like the passive house level for the window components. So that's why regulations are focusing on the building enclosure generally, and that naturally ends up putting our attention on windows more than almost anything else. And there's whole bunches of examples, thankfully, all over North America now, where either building codes have recently changed or are about to change or are developing their changes. And the neater thing than the fact that this positive movement is gaining traction and momentum in the regulatory world is the way, at a more detailed, more physics-based level, of how it's happening compared to how it's been happening in the past. And by that, I mean the way the actual codes work when it comes down to our level of practicing building design with these codes. So in the past, previous energy codes, an example might be ASHRAE 90.1, had a number of compliance paths for you to design the building and show that it worked, but they all included, or were even in some cases based upon the idea that if you have performance targets for each of the assemblies, for example, an R value for the wall and a different R value for the roof, and yet another R value, or more specifically U value, for the windows. If you had these things and you met these targets, then by some miracle, the entire building would work, even though we don't have, in this case, an example of the performance where these assemblies meet, or really a built-in requirement for other characteristics of the building, the air tightness or anything like that. It would be like trying to take the ingredients that would make a cake, and if you have them in the right proportions, it doesn't really matter in which manner you combine them, or even when you bake them, you will undoubtedly get to the end result you want, just having the right ingredients. And well, we all know that's not the case. The newer energy codes that exist, and in my region of the world, in British Columbia, Canada, there is a new energy step code, which is fairly similar to most new energy codes that have either been most recently adopted or will be in the next iteration all across North America. These codes work differently than the past recipe-based code that had individual targets for assemblies. These new codes have an overall target for the amount of energy that the building is allowed to consume per year. There's technical terms for it, but the way I've often explained it is, it says, the energy code says, you have this one total amount of energy for the year based on the floor area of your building. There's your bucket of energy. Use it any way you want, but you can't have more until next year. And then the next step is, well, if we make the building enclosure much more efficient overall, if we make the whole building perform better and leak less of that energy out of the building enclosure, we'll have more of it left over for all the other cool stuff we want to do, like have big screen TVs or have just whatever we want to go on inside of the building. So this builds in a couple of things that the previous codes did not. Number one, it builds in a whole ton of flexibility now. You don't have these stringent targets you must meet. But with that flexibility comes the responsibility of the designer and the builder that once you create this new building, the results really matter. How you got to the results was up to your own expertise and choices, but the whole energy use limit for the building is just one target. So I want to do a couple of calculations for people who are really interested in numbers and want to see an example of that work out in real life. And to do that example calculation, I'm going to go on to a tool that's on the Cascadia Windows website, which I bet a lot of people on this call could actually make with an Excel calculator in just a few moments. But I'm going to use this simple area weighted calculator to look at walls, windows, and roof and assign them both an R value and an effective area. And to do this, I want to suggest a type of building and a target that that building might have. So for North America's sort of average current energy code requirement, if you were to build a new multifamily building today, and you were to have, well, I'm going to get to ratios of windows and walls in a second here, but if you were to have at the very early stage in design, an R value target where the building will likely end up the way you want it, if you start at this target, that number is probably going to vary somewhere between about R7 to 10 overall. That doesn't sound that high, but if you compare it to the last 3 buildings where I said to everybody, please guess the R value, and that's a heck of a sight better than we've been doing for a long time. I'm going to suggest for the wall R value that it's about an R15.6. Why that number? That comes out of the prescriptive requirements of the ASHRAE 90.1 code, whether it's still in force in your jurisdiction or not. And I'm going to say that for this hypothetical building, this new multifamily building, there's twice as much wall as there is window, 2 to 1 walls to window. So since we're going to have a roof, I'm going to make a little bit at the end of roof, and the roof can be better than the walls, thicker insulation, let's say R25, and these are effective R values. And then this multifamily building would traditionally have a thermally broken double glazed aluminum window system in it. Whether that's good or not, whether that gets us to where we want to be or not, that's going to end up performing, if you consider the doors, the windows, the sliding doors, the frames, and everything combined, it's probably going to be about an R2 effective, or a U value of about 0.5 or modestly better than that. I'm going to assume it's going to be slightly better than that. So I gave it an R2.25. It makes the whole building have an R value of just over 5.5. Okay, so that's not at that level of R8, or even, let's say, that range of R7 to 10 that I had suggested just a minute ago. If you needed to get there to really lock in this design early stage and say, yes, we are likely to end up with energy code compliance. What if you were to try to get into that R7 to 10 range by doubling the insulation thickness in the wall? So we've gone from about R16 to R32, and it's the biggest amount of area on the building. We've added R16 to more than half the building. We've added a total of less than R1 to the whole building by making this change. So not a lot of bang for the buck there. And for the roof, we could add R25 trillion to the roof, and it wouldn't make any difference at all. So if you look at the window, well, the window is more of not an assembly so much as it's a product. So you have more limits here, but in that product, there's glass and frame. And since the frame tends to be the weak point, if you change the frame material to a composite material instead of the aluminum example that I started with, you'd have the effect of bringing the window's R value up to around 4, or that would be a U value of about 0.25. What have you done to the whole building by adding less than R2 to the windows? You've increased the R value of the whole building by 3 by adding less than R2 to just the windows. So this is very significant. This is the outsized proportion of heat loss that occurs at the windows because they are the weakest link. Now, that's interesting in and of itself because it gets us to where we want to be for this example. But I want to take this one step further. If you had, let's say, another layer of glass in those same windows, now it's a triple glazed unit instead of a double glazed unit, which is readily available these days. Your R value is so far and beyond where we said we wanted to be in this hypothetical example that you could do something really fancy that would make your developer client really, really happy about this window design. And instead of saying we have to have 60% walls and 30% windows, let's switch those. Let's have twice as many windows as walls. And at this level of performance, we are still where we want to be from an overall building R value perspective. We are still set up for energy code compliance. So I'm going to switch back to the slide deck now, but that's an example of the math behind why increasing the performance of a window will have such a significant overall effect on the performance of a building. But it's not just having a little bit smaller heating bill, it's doing something like this. It's doing something where if you could make a code compliant building with an aluminum window frame and have a certain amount of glazing percentage, let's say 40% glazing percentage, could you make that building have a more valuable amount of glazing percentage in terms of people enjoying their view and still end up with compliance with the most stringent energy code? Yes, you can, if you use a higher performance fenestration system as a tool to get you there. So another poll that I want to launch is how familiar are you when I say a fiberglass framed window? Have you heard of that before? All right. Thank you everyone for clicking into the polls. Okay, so there's everybody. And I'm very happy that I'm talking to a familiar audience. This is brilliant. Now, from a technical perspective, if I say fiberglass or I say composite, what I really mean is a window frame that has a fantastically high thermal performance based upon its material. So from an educational perspective, we don't have to focus exclusively on fiberglass. I'll provide a bit of information about what does make a fiberglass window special, because there are some differentiating material characteristics. But unless I say that, just think composite window frame. So fenestration systems generally, what are some of the differences between the system types, not just the materials that are used to construct them? Well, like we said in the beginning of the presentation, energy wasn't always the focus of both manufacture and engineering improvements in building envelope consulting and building envelope product manufacturing. In the past, in the recent past, it was improving the reliability and the robustness of the water penetration resistance. And this slide has been ripped screaming from an educational presentation of a few years ago. These different fenestration systems include storefront, which we're all familiar with literally at the front of stores, and was typically never designed in its original conception to be a very good water penetration resisting system. So a lot of water to be concerned about using those systems, especially in an exposed environment. Now, punched windows, there actually exists a great range of potential water penetration resistance in punched windows. Punched windows could also be strip windows, which is essentially a punched window with a detail on the side of its frame, which enables coupling together of multiple punched windows in order that the resulting product is a strip. The two other window systems exist, which are more often found in commercial and high-rise construction. Those are window wall and curtain wall. They both have the visible features on the outside of concealing the structure that they may be attached to or that they may actually be positioned in front of. The most significant difference is that a window wall is a one-story high window system, kind of like a strip window system, but a portion of its frame extends down from its sill to cover the structure that each one floor level of windows is sitting upon. Whereas a curtain wall is a construction of window framing tubes that are connected to the structure through brackets that hold them fully outboard of the structure, and it hangs like a curtain. We're going to end up talking about punched and strip windows as the example in the first portion of this, and we're going to get to window wall and curtain wall. But I want to expand upon the window wall and the curtain wall discussion a little bit more so that you can picture in your mind, once we get there, what did some of these products and product features and components look like? Well, window wall and curtain wall fenestration systems have robust water penetration resistance, mostly because of the design of how they manage moisture. They have a rain screen designed to their ability to manage moisture. They have a water shedding surface on the outside, and they have a water resistive barrier on the inside, and it transitions from glass to frame to membrane at the structure, and then back to frame, and finally back to glass. The curtain wall has the same features, but the positions and the components differ slightly. The surface that the glass touches on the curtain wall travels through the tube. It may travel through a back pan at an area where you cannot see through the glass, for example, outboard of a structure, and then back to the vision glass. Both of these types of systems can run between multiple stories and accommodate the building movement that exists in those stories. Unitized products are curtain wall systems that have been assembled into modules in a factory and then brought to site and fitted together on site. These can be very large modules. If you are talking about a curtain wall system that's not unitized, then it's instead stick built. It's assembled tube by tube, almost like a framed wall in the field, and glass is installed as one of the final steps. All of these systems have the same approach to how they physically manage the elements, how they achieve airtightness, how they achieve water penetration resistance. So that was just a few slides to characterize the difference in types of systems. And like I said, we're going to talk a little about punched windows and a little about these more commercial systems. A lot of what we're going to talk about, though, has application in both scenarios. So for window design, we're going to look at what a high performance window might look like at a more detailed level. So if there's any physics geeks amongst us on this call, you'll appreciate the next few slides. But before we do that, I just want to find out what's interesting to everybody when you consider specifying or simply exploring and looking for a window product during your normal practice. Pick up to 3 characteristics that you find are most important. All right. I'll give everyone another 8 or 10 seconds on this one.
It only allowed us to choose one.
Oh, choose one. Okay, well, I apologize for suggesting that the poll would do more than it truly does. That's fine. I hope everybody got to choose the one that they focused on the most. And I'll share these results here.
It didn't allow us to choose water resistance.
Water
which is the
penetration
first one
resistance.
for me.
I'm glad that you added that. Our company was started by a group of building enclosure engineers and window specialists who focused first and foremost on water penetration resistance. So I share your interest in that necessary topic. Nevertheless, maybe that's an improvement that I can make for the poll section of future presentations. All right, so regardless of what was most important to you through in that little poll, I want to acknowledge that since most people, actually an overwhelming percentage of people, chose thermal performance, about 80%, thermal performance can be achieved at close to the highest levels with all 4 of the today's common and readily available window frame products. High performance is not exclusively reserved for only 1 or 2. That being said, the base material of the frame does make it more convenient in terms of product design and fabrication and cost if it is naturally more insulative, or more specifically, if it conducts heat as slowly as possible. But nevertheless, you can get passive house level performance out of window systems that are made mostly from wood or plastic and PVC, or fiberglass or aluminum, more specifically, thermally broken aluminum. Now, there's different applications for these. That's why they all exist. Wood windows these days are more commonly than ever, or most common.
Is it just me or did he freeze?
Yeah, He froze and I don't hear anything from him.
Okay, let me tell him that. Oh. All right, give me 1 second. I'm going to call him. I apologize. He's logging back on now. Okay, can you hear him? Because we actually do have a question while he attempts to log in. All right, so the question was curious, what is the % of projects that are actually using and installing triple glazing currently? Sometimes I see it specified, but then often it gets axed due to VE.
Yeah, that's a good question. So the amount of projects that triple glazing will survive the VE project or process will vary with location as well as with the objectives, the energy performance objectives for the project overall. So the physics behind specifying triple glazing makes all the sense in the world. It is the most cost-effective way to improve the whole building's thermal performance. However, in cases where the whole building doesn't actually require thermal performance, for example, for regulation purposes, then you end up in a situation where if it's just ideologically driven, triple glazing is only going to survive the VE process while there's money to buy it. Whereas if it is a tool used to achieve regulatory compliance,
then in that case, the triple glazing will definitely survive.
Very well, it seems like we're back online.
We're back online, and my apologies for the technical glitch at my end. We are picking up where we left off there. And I will share my screen, and away we go.
Well, thank you, Ken. Great question.
Yeah, that is a great question. So Sarah, is it shared screen back going again?
Yep, you're all
Excellent.
good.
So cost and triple glazing going hand in hand is definitely a life cycle, a selection criteria. There's also life cycle cost built into the topic of cost, not just the line item of the window product and the things in it, such as triple glazing. It's interesting when you look at considerations for selecting a window type, such as weather resistance or the physical features of a curtain wall or a window wall. You will naturally trend towards different materials, and that's okay. I want to look to show you a few features that end up bolstering a window product's thermal performance, because everybody or almost everybody indicated that that's one of the key features they're looking for in design. So what are you going to see in the broad cross section of window supply if you start looking at the features that indicate a window has been designed to have or at least have the option of high thermal performance? You're probably going to see an option for triple glazing. If that triple glazing has a greater width to it than double glazing, then that product has truly been designed to deliver the most good of triple glazing. So if you are used to specifying windows that have, let's say, 1/4 inch thick glass and a 1/2 inch thick airspace, your double glazed unit would be a width of 1/4 plus a 1/2 plus a 1/4 would be about 1 inch. If you added another airspace and another piece of glass, logically, you then have a unit that's about 1 3/4. And that's generally where you want to be in terms of having a high performance triple glazed unit, instead of a window manufacturer that has taken a window that's designed for a double glazed unit and tried to cram a triple glazed unit into that same narrow cavity. That will thin out the unit so much that the performance will be diminished. What are some other physical features of window products you'll see that suggest high thermal performance? You're going to see options for glazing systems that have warm edge spacers, whether they be stainless steel or thermally broken or all non-metal spacers. You won't have the typical solid aluminum spacer as a product option. You're going to see multiple gaskets. You're going to see, instead of the 2 typical gaskets on an operable window, which include a gasket on the outside as part of the water shedding surface and a gasket on the inside, which is the air barrier and water resistive barrier gasket, you're going to see at least a 3rd gasket. What is it doing? What is its job? We've taken care of water with the first 2, as long as we drain the space in between them. So the 3rd gasket is existing there for thermal performance improvements. And regardless of its exact shape or its exact position, in general, a 3rd gasket just has the function of dividing that relatively large space up into 2 smaller spaces, and there's less transfer of heat because there's less movement of air in those 2 smaller spaces. So you're going to see multiple gaskets. You're also going to see insulation designed into the frames. Sometimes you'll see it in all the frame cavities. Sometimes you'll just see it in a couple of strategic cavities. If your work involves site review and the window products that are coming to your job site have opened frame cavities, I encourage you to, at least at one time after the window installation has just started, inspect for the presence of that insulation. If that insulation is part of the model and if it's part of what the building owner is paying for, then it ought to be there and it ought to be as complete as the window manufacturer is suggesting in their advertising, as well as their thermal modeling results. You're going to see multi-point locking hardware on these systems. That's not necessarily going to make them better from a thermal perspective, but it's going to make them lock more consistently around their perimeter, and that will improve their air tightness. Air tightness is a big deal, but when you're selecting a window, there's not really much you can do from an air tightness perspective other than trust the manufacturer and do a little of your due diligence that their test results are reasonable and consistent for their product line. Minimize frame area is nice. It's aesthetic. It's one of the things that I would suggest that fiberglass and aluminum systems probably do better than PVC or wood, just because of the inherent strength of fiberglass or aluminum. And does your product need to be double glazed or triple glazed? Well, that's just going to be decided based upon the mathematics involved. But when I said before, just an offhand comment that double glazing to triple glazing is the least expensive and most significant thermal improvement you can make for the whole building, that's actually true. The amount of heat loss is reduced by about 40% of the total heat loss through a window simply by going from double to triple glazing in a window that already has a relatively high performance frame, like a composite frame. And similarly, to go from a typical triple glaze to something that you might label a premium triple glazed unit, it's again a smaller step, but if you're into net zero or passive house design, these options exist for you in our industry. Now, most people would correctly think that higher performance windows are also going to carry at least some cost premium. This is natural, but there are things you can do, especially if you are either involved with the design of windows or you can influence the design of windows when the project is being literally drawn. So how do you save money with your pencil? Well, simplify it. Now, I want to speak from our company as an example here, for better or for worse. So these pieces of advice won't carry over equally to all window manufacturing companies. They definitely hold true for fiberglass framed windows, but they'll help you in any sense, no matter what type of window it is. If the window systems can structurally take it, then in the design of a window that fits a given rough opening, if you have less window framing passing through that rough opening, so you can take two verticals and make it one, you will save money. There's also potentially two other benefits you would get here. Benefit number one, you would decrease the amount of interruptions in the sightline, so the view's better. In addition, you would decrease the amount of framing material, which we already said is thermally the weakest link. If you can reduce the amount of framing material, and even a step further, then you can reduce the amount of weak link components that are in your insulated assembly, your window. This is kind of taking it to the extreme. And if vertical frame members are part of your building's design, go nuts. But having less operables and having less framing, especially for products that are hand assembled by technicians as opposed to machinery, that's definitely going to be a cost optimization. You can also make them bigger if you're dealing with fiberglass and aluminum compared to PVC, for example, just because the material has the inherent strength to make that possible. Okay, I'm not going to belabor this point. The punchline is, for saving money, have only the number of operable vents you need, not more, for the fun of it, and have as many frame members as your design calls for and the window calls for structurally, but not more than that. Try to economize on the number of window frame members.
I have a question about size and thermal performance.
Yes, please.
With aluminum framed windows, you actually get better performance by increasing, because less of the overall area is the poorly performing metal. But
exactly.
It kind of, if you're saying that a triple glazed fiberglass framed window is R7, then that means that the frame and the glass are almost the same R value. So you don't get, you don't get as much improvement of thermal. I mean, you already get a great thermal performance, but the number of mullions doesn't have as much impact on.
Yes,
correct?
Yes, that's absolutely correct. And thank you for putting that math into words. So for everybody who didn't understand that as intimately as Greta there, the thermal bridging that is diminishing the performance of the glass caused by the frames is more significant in aluminum, which means that if you eliminate aluminum framing, you preserve the performance of the glass better and better. And yes, fiberglass framing is darn close to the center of glass performance, which means you don't drag it down as much. So the reason why I've encapsulated these last couple of slides as cost optimization advice as opposed to thermal optimization is exactly for that reason. The thermal optimizations they exist, but they're minor in a high performance window frame like a fiberglass frame or a composite frame. Whereas the cost optimization is significant, like significant. If you took this window wall module that is shown on this final slide here, and you were happy with the product that's shown on the right-hand side, filling the hole compared to the one that's shown on the left-hand side, you'll probably get that same glazed area for 30 to 40% less cost, whether it's double glazed or triple glazed. And let me comment on a couple of other aspects of windows in the envelope that go above and beyond just the product or the type of frame. Air leakage is a very significant focus, and when it comes to the window, there's the least you can do for the window product itself. You can do a lot for the building around the window, and the simplicity or the complexity of the building around the window will make detailing and sealing the windows into the building envelope either harder or easier, less repeatable or more repeatable. But from the perimeter frame inward, you kind of have to trust the manufacturer you pick. But you can also do yourself a favor when you're looking at how opening windows operate. Somebody who wants just an engineer who wants the best air tightness in the world would say, well, don't have operable windows and they'll be very airtight. While that is true, that's not much fun. So if you have operable windows which slide versus swing, the swinging window will tend to have better air tightness because when the window swings closed, it compresses its gasket seal like the hatch of a boat, instead of a sliding window, which just uses friction against a piece of sliding weather stripping and will tend to have an inverse proportion to how easy is it to operate this window compared to how well does it seal. And in any case, will not seal as well as a window or door that swings shut. Another thing, when I say you trust your manufacturer, this is a copy and paste from one of our operable windows lab tests. The machinery rounded to 2 decimal places when testing air leakage and reported 0.00. If a manufacturer like us sends you this document, what can you do with that? Well, I mean, it's bragging rights from the manufacturer, but when you're thinking about a specification, a technical specification for your project, where do you have to tap the brakes? Somewhere before you take an example like this from someone like me and say, well, I'm going to specify that the windows shall have 0.00 CFM per square foot air leakage, no matter how we test them. Well, that's not realistic, and that's not the rating that they're certified to. That is the reported results of a window that was tested. So it suggests that that product or product line can and may frequently be way better than the allowable requirements, but you have to tap the brakes before you specify that as the air leakage for the whole project, because the allowable air leakage rate for windows is a certain measured amount. There's going to be some air leakage somewhere. We're talking about a product that's manufactured and installed by humans. So that's the comments I wanted to share with that screen grab. Other aspects of windows that are a little bit out beyond how products are built, well, shading and solar control is a big deal. And there's different ways to address shading and solar control. Some of those ways don't involve the window product itself, and some of them exclusively involve the window product. So to just acknowledge them, yes, building orientation, building form have a great deal of influence over the amount of sunlight the glass will be exposed to, and therefore could allow to come into the building. You can address that with coatings on the glass as well, low emissivity coatings. And you can address some aspects with interior shading. However, let's look at the 3 different things you want to try to control with the optical things that you want to control. So you want to potentially be able to control privacy and glare and solar heat gain. Overhangs on the building, they don't control privacy, but they definitely can control solar heat gain if you can shade the summer sun. Exterior shading. Exterior shading does a pretty good job of all three of these, actually. You just can't see out once you deploy it. Glass coatings, low E coatings. Well, low E coatings won't provide you with much privacy, but they will have a pretty good reduction of glare and an excellent reduction of solar heat gain if you select a low E coating that is optimized to do so. Window manufacturers will generally offer a menu of potential low E coating products that you can specify with the glass, and they're usually all similarly priced. This is usually not a price point conversation. These coatings will allow you to either have sunlight come in, heat gain through the glass, or rejected, heat gain reflected away from the glass, depending on what you specify. Interior shading, good at privacy and glare, does not control solar heat gain. Interior shading will get hot because the sun comes through the glass and is already in the building. So interior shading, yeah, you won't be sitting in the direct sunlight, but your room will be experiencing all of the heat from it. Now, how about,
Sorry
oh, please go ahead.
We do have one question before we get too far.
Yeah.
On. Ryan asked, is it common to have sliding doors that have a compression seal? Yeah,
good question, Ryan. And I think you're sort of setting me up to flog my own product a little bit there, but it's not the only one like it. Sliding doors do not typically, if you take the industry as a cross section, sliding doors typically don't have a compression seal. Instead, they simply unlatch and they slide and they press against the friction seal. People in the industry would know that that's called a mohair gasket, just a gasket with little hairs that touch the part that slides. That type of gasket will deteriorate a little as it wears over time, and in any case will always be a compromise between how easy does it operate compared to how does it seal, if at all. There are doors, and our company makes an example of them, which, because of the action of the hardware, allows the sash of the door to be like the sash of a door on a swinging door, where it moves away from the gasket, or if being closed, it clamps against the gasket. But the action of the hardware of our sliding door, and others like it, is that once you release the hardware, the sash pops away from the frame, it projects away from the frame several inches, enough for it to slide past and either in front of or on the inside of the fixed piece of glass beside it. So this offers the best of both worlds. You don't have friction at all while the door is being operated, but you do have compression seal on all four sides once the door is locked closed. So thank you, Ryan, for that prompt. I want to offer the last bit of advice when it comes to selecting doors with things like air leakage and water penetration resistance in mind. If you took some of what I said about a compression seal and applied it to a swinging door, because we just talked about sliding doors, a swinging door would generally perform better with a compression seal that is on all four sides. It is common to have lower priced swinging doors with a friction-based or sliding seal, a sweep at their sill. However, a door that has a compression sealed gasket at its sill will generally perform and outperform any other door that only has a sweep. The trade-off is that there will be at least a small vertical step. So if you can tolerate a small vertical step with the design of your swinging door, then that is to your advantage, because it will give that door product the ability to have a compression seal at its sill, not only its other three sides. Again, Ryan, thank you for prompting that. I'm going to skip ahead here to a couple of other topics. Actually, I'm going to go through this topic and skip the deep dive into why fiberglass, because I think this is probably more interesting as a broad look at windows generally. When it comes to taking considerations about the building enclosure and considerations about the products, and we've covered sort of those already, how do you connect them? Well, you connect them in a way where you want the products fastened, supported, and sealed. Well, let's tackle the first one, fastened. You generally have a product that has a nailing flange, a part of the frame that projects away from it and overlaps the wall of the building, or you have an anchor, a system of components that allow the fasteners that connect the window to the wall or to the building structure generally to extend inwards from the window and be attached to the structure. These are particularly convenient on larger scale construction because they facilitate installation from the interior side of the window. But they do more than help for a more versatile, safer interior installation. They accommodate things like we know buildings do, like movement, better. And as soon as I explain the way that they accommodate movement better, you'll appreciate that that ties into the discussion about air tightness and long life of building installation details. So they accommodate building movement better. What ways do buildings move when it comes to a window product? Well, buildings move to the side, either in a little bit in wind or a lot in an earthquake. Buildings also move from a floor to floor level. They move downward. They deflect because of load. So a window has to take both of those. So horizontal movement from wind and seismic forces, downward deflection from live loads and dead loads. So when you're talking about the first one, horizontal drift, you've got an opening in the building, no matter what its size and shape is, and you're putting a rectangular window product into that opening. And then the building moves. And our hope is the window doesn't. You want that rectangular window to stay a rectangular window. It's good for it. You don't want it to become a parallelogram. It's not good for the air seals and water seals in that product. So you have a gap around your window that is intended to allow the building to move and the window to stay the same. This should say vertical deflection, just a typo there. Vertical deflection is that same gap being consumed by vertical movement. Again, you want the window to stay as a rectangle. I have a personal bias towards strap anchors as being the more accommodating of the two methods that windows could be attached to a building. And I feel as though nailing flanges are a less tolerant approach, although they still can be successfully used. A nail flange, to be fully successful to accommodate both of those types of movements, would need to have horizontal slots at its fastening on the sides of the product. And even though these vertical slots look a little distracting at the head of the window, you would need to have a second overlapping component, an extrusion that overlaps this flange that allows for vertical movement and horizontal movement at the same time in order for this attachment approach to accommodate all building movement. Now, if your attachment approach accommodates all the building movement, it's more likely to allow the seals to continue to be sealed, both in the product itself as well as to the wall over time. Here's an example with a strap anchor. A strap anchor achieves an unlimited amount of building movement if it is designed in such a way that it will slide within its frame. These type of anchors are more proprietary from one system to the next. This one is obviously our company's. It embodies that ability to slide pretty much infinitely. So when you attach strap anchors to the building, the anchor moves with the building, but it doesn't transfer all of those movement forces into the frame itself. It allows the frame to stay as a more whole rectangle. And I'm going to wrap up by talking about sort of the future of installation. I'm going to skip past a little bit here, so you're going to see the slides flutter past us in a second here until I get to a few of the case studies. When we're installing windows and we're looking at and acknowledging the benefits that high performance fenestration can give us, not just to make a more desirable building, but also to achieve regulatory compliance. And we look at these improved walls and we look at, oh, we can even connect them now. We can connect them with strap anchors. And where you connect them in the wall is quite significant. And what I mean by that is aligning the high performance window with the most insulated layer of the wall will make or break the performance of that window that you're paying for. If you were to have a window that's situated on a structure and outboard of that structure, you were to have insulation and a point where the insulation hardly or doesn't overlap the window frame, then your installation detail, not the window itself, is a thermal bridge. And in this case, you might as well take that triple glazed window and double glaze it. It is going to be that significant. So the solution is to work to move the window frame into at least part of the insulation layer. But that creates new challenges in detailing that as an industry, we're not used to fixing. And I want to show you a real case study because we're out of time to go through some of the rest of the content here. I want to talk around a case study that was never intended to be a case study, but it turned out that way. And that's the largest passive house retrofit project in the world that was just certified in Hamilton, Ontario, just north of you guys. So this originally was just a not so interesting concrete structure of a building with brick as the exterior veneer, had some concrete balconies, was used as social housing, and the building became in quite poor condition. They eventually just evacuated everybody and they went to work redesigning and retrofitting the building to become Passive House certified. They did a couple of very interesting things, such as cut off the balconies on the exterior for a variety of reasons, but the main one was the thermal bridging couldn't be solved any other practical way. And then they went to work on the windows, and the windows in this particular construction needed to be situated outboard of the concrete wall enough that the exterior insulation that was being installed over the opaque wall would come up to and all around and touch the sides of the frames. And in this case, these are our company's windows, so we're talking about a fiberglass frame. It is usually not necessary to press insulation up against the entirety of the side of a window frame to thermally optimize an installation detail. But if you want to thermally optimize an installation detail with a thermally broken aluminum window, you have to have the insulation fully touch the side of the thermal break. You don't get to just cover the front aluminum. It doesn't work that way. You have to touch the thermal break. But a fiberglass frame window is basically like a thermal break throughout the entirety of it. So as long as you overlap about half of it, that's usually enough to optimize your detail. In this particular case, they were down to the very last digits in the mathematical equations. They needed to overlap the whole frame. And what that turned out to mean is that the window frame needed to be outboard of the structure. In other words, the inside of the window frame is flush with the outside of the structure. So you've got triple glazed windows, you've got 1/4 inch thick glass in almost all of these. How do you support that weight? That's 10 pounds a square foot. From a structural perspective, in the big picture, that's not massive, but when we're talking about small human-sized components, that's quite a bit. Well, if you went to a structural engineer and you didn't say anything about thermal performance, you just said, here, 10 pounds a square foot, support this window on the outside of this concrete wall, they'd say, well, this is no problem. Put this metal L-shaped angle under the window, it makes a shelf, the shelf will support the window. Great. But the metal can't work in passive house or highly energy efficient project because it's too much of a thermal bridge at every single window. So what do you do? What would you do? Well, you'd look for a material that can support the window in a similar way, but the material needs to be a low conductivity material so that it's not a significant thermal bridge. And these designers selected a big, thick fiberglass angle for this purpose. And then they delegated the design of that angle to us, Cascadia. Hey, glazing engineers, you guys specify the thickness here, send it. And we did, and they mocked it up, and they realized that the 1/4 inch thick angle that we provided was too flexible to allow the windows to be flat as they were installed and coupled together. It was 6 times as strong as it needed to be for its actual calculated loads, but nobody that was installing these angles or calculating the loads on them realized that fiberglass, while super strong, is much more flexible than the aluminum angles that would have been historically used for this purpose. So they bent too much, and the angle had to be changed out, and ultimately a 1/2 inch thick angle was specified and used successfully instead of the 1/4 inch thick one where we started. I'm not going to finish this little case study, this little story with a good news conclusion that gives you a nugget to go away with, because we didn't come across one. We just understood that the evolution of high performance products and high performance buildings is going to, as it matures in our North American industry, it's going to cause challenges where we want to do something where historical materials would have made sense, but for energy efficient reasons, they no longer do. And that's going to be occasionally tricky. You're probably going to encounter this and be involved in it. And hopefully you can sort of sit back after the initial stress of those types of situations and say, well, you know, that's just part of the industry moving forward in a scattered way, in a painful way, but it works out. And this did work out. And we were happy to be involved in it. And I think we're pretty much where we wanted to be from a time perspective. So I'll finish with just the last little case study here. The window wall style products that I described before that cover the structure that they're placed upon, so as to have the opportunity to make an all glass building. Cascadia used its experience in fiberglass window frames more recently to create really the world's first fiberglass framed window wall. This product is used in instances where the thermal performance of a fiberglass window system is necessary for the performance goals of the project or the regulatory compliance of the project. But the design calls for a commercial window system look and function. So this particular project, the Chelsea, is a two-building multifamily complex in Vancouver, British Columbia. It was the first large-scale project with this product on it. 4 or 5 have followed since a couple of years ago when this was completed. But now that product exists, and it's helping wherever it can from a regulatory perspective. So key takeaways. Windows have a really big impact on not just thermal performance or making for a slightly smaller heating bill, but since they're the weakest link in the building's envelope, little extra attention on window performance and the installation of high performance windows can have the largest overall impact on the building, which leads me to pay attention to the product details itself. You need to verify the product details and the performance that you're looking for, and that you're specifying those products in a way that can be delivered. The glass units can be delivered, the extent of reinforcing necessary in those products will match the advertised performance that has been given to you to rely on in calculations. And then finally, like I started off with, high performance window systems can actually lead to not just better buildings, but more design flexibility as you go, because the rest of your building doesn't have to make up for them quite so much. So thank you everybody for logging in today, for even tolerating our little technical hiccup, and for being with me through this learning session. We have lots of time, should we need it, for questions and answers. So I'd encourage you all to go ahead and either jump in on your microphone or write a question for Sarah to read out.
We do have a couple of questions. One of them was, are there flame/smoke spread or NFPA 285 concerns, specifically when using a fiberglass window? Anything out of the ordinary as opposed to aluminum windows?
Good question. So the simple answer to that is no. There's no difference in America using fiberglass or other composite window systems compared to how you'd use aluminum window systems, with an exception. So now that exception. In the case of a curtain wall window system, an aluminum curtain wall window system is a window system that hangs in front of the structure. Remember that earlier slide, whereas a window wall or a punched window or strip window sits on the structure. So in only the case of an aluminum aluminum curtain wall, the aluminum curtain wall, because it's hung off the outside of the structure, and since that structure delivers the fire rating of that floor assembly, that structure needs fire stopping materials installed between the outer edge of that structural slab and the back side of the the curtain wall framing system. That fire stopping is installed, but it interacts with, it is in contact with the curtain wall framing, and therefore it involves the curtain wall framing in that floor assembly's fire rating. Plastic, wood, and fiberglass, or any composite window system would have to obtain the same success in testing that traditional aluminum curtain walls do in order to be used in non-combustible construction as a curtain wall. But window walls and punched windows and strip windows and storefronts are not curtain walls, and they're not subjected to those requirements. They can be any of those window frame materials. Good question.
And then we have one more. Have fenestration assemblies with composite framing been tested according to NFRC?
Yes. So for everybody's background that doesn't understand the details within that question, NFRC stands for the National Fenestration Rating Council, and it's by far the most thorough approach to objectively claiming the thermal performance of window systems, typically punched and strip window systems in North America. And as an example of a fiberglass framed window, all of our fiberglass frame windows are NFRC tested and certified, including the fiberglass framed window wall system. The other fiberglass framed windows that I'm aware of manufactured more in Canada than the United States, but probably sold more into the United States even than in Canada. All of the companies that come to mind that I'm aware of have at least a good proportion of their products and their major product lines NFRC tested and certified as well. But I can guarantee you that Cascadia is an example of one that does, and you can find it on NFRC's website. So thank you for that question.
Great. I think that concludes all the questions, unless anybody else would like to speak up. Oh, one more. So Ryan said, to clarify regarding fire testing of the fiberglass punch windows, tests have been done illustrating comparable performance to aluminum, correct?
Ryan, you're using a little bit of our prior knowledge to plant a question that has a very interesting answer to me, because I'm enthusiastic about it. The answer is absolutely yes. There has been physical testing done, not for the benefit of users and specifiers in America, because Americans' building codes already correctly address the requirements for the fire performance of windows and doors. However, Canada's building codes unfortunately do not. They have some old limits in the building codes up until very recently that were based on sort of arbitrary decisions more than half a century ago. But in order to change those, we had to develop our industry needed to develop some evidence on which to base to base a building code change. So what was done over the last few years as part of an industry cooperative with the National Fenestration Rating, the National Research Council of Canada, is a substantial amount of testing where it culminated in a large-scale fire test. I'll just show this slide full screen, where similar in concept to the NFPA 285 test, which tests for a multi-story combustible facade. The S134 test, which is kind of like the NFPA 285 on steroids, it's bigger and uses twice the fuel. It was used to test, well, in this case, fiberglass frame windows, and the fiberglass framed combustible window frames were permitted to burn up to this green line for flame spread, but not beyond it. In fact, only burned about half that way up, and by the end of the test, self-extinguished. But we also were able to compare that to thermally broken aluminum windows, which, because of the thermal breaks, are combustible. All windows are combustible: aluminum and fiberglass and PVC and wood. However, thermally broken aluminum windows, while being combustible, did pass this test and are safe. But by extension of the same logic, fiberglass windows and composite windows are also combustible, also pass the test, and are also safe. And this testing formed, and the engineering behind it, and multiple tests like it on different materials, led to a building code change in Canada that has just been published less than 2 months ago, which now reads, instead of having arbitrary limits, just says combustible window sashes and frames are permitted in a building required to be of non-combustible construction, provided they are vertically non-contiguous between stories. So that that kind of relates to what I was saying before, that prevents wood or PVC curtain wall from being used unless it were subjected to the same tests that metal curtain wall has been in the past.
Yeah, that's a great question, Ryan. I'm glad that you had a second presentation to even show us what the test was like.
Yeah. And if anybody on the call is interested in this particular topic and the thought process behind how the Canadian industry got there, it is one of our company's webinar offerings that are available on cascadiawindows.com and do carry AIA credits if that's important to anybody.
So I think our concluding question from Greta is, what type of composite materials other than fiberglass are used for framing?
Yeah, good question. So the four major framing materials are, I'm just going to navigate to the slide in case we have a bunch of visual learners here amongst us. They are wood and PVC and fiberglass and aluminum. I like using the term composite framing systems because it seems less proprietary. Makes me sound more like an objective educator than a salesperson working for a fiberglass window manufacturing company. However, I really mean fiberglass or structurally similar materials that have the same thermal properties. So what you could extend that definition to is a reinforced PVC window, or you could extend it to a thermally broken aluminum window, which, while it's aluminum, its inner and outer edges are pretty much only aluminum, and what exists in between is a sophisticated plastic thermal break. Those different plastics have different chemistries. Some of them are polyamide, some of them are UPVC, some of them are even fiberglass or fiber reinforced versions of those plastics. And further, some of them are simply PVC windows reinforced with fiberglass, similar to a chunk of this frame. So I like to use a more generalized term, composite windows, which is sort of a non-metal window. It is a polymer-based material having low thermal conductivity as one of its key properties. But in terms of what framing materials you're going to find out there when you shop for products, you're going to find one of these four.
Great. Well, thank you so much, Michael. We really appreciate your presentation and the time that you took to put this together, and also giving it from, a different part of the world is pretty cool, and I guess a blessing from Zoom. So until next time, is nice, I guess, meeting you.
Thank you very much for hosting and inviting us, and thank you everyone for tuning in. Have a great day.
Very informative. Bye-bye, everyone. Have a great night.